Hey there, my name is Josh Bloom, and I am a PhD candidate in the NEST Lab. And today I'd like to share with you some exciting work on multi-agent reinforcement learning. Now we're very interested in cooperative problems, where agents learn to work together in pursuit of a common goal. Warehouse robotics, search and rescue, and collective transport are all great examples of cooperative problems. In multi-agent learning, the robots are typically assumed free to move independently. However, common applications for multi-robot systems include modular robotics and collective transport. And in both cases, the robots form and disband aggregates dynamically, depending on the problem at hand. Research on aggregate robotics is currently in its infancy due to the difficulty of studying exact mathematical solutions that generalize. Reinforcement learning is a promising way to tackle these problems, although very little work exists. Now here we're going to showcase the potential of reinforcement learning by solving collective transport in environments where obstacles are present. And we show that it's not even necessary for the robots to communicate directly. Now this is because of the physical constraint of being connected to the shared object, and it's sufficient for coordination to emerge. There have been several works looking at solving collective transport tasks using reinforcement learning. From characterizing independent learning and centralized learning, to implementing macro actions, to using curriculum learning to learn complex tasks, and even looking at oversized objects. But here we present a novel approach using belief state over the entire system, and learn to forecast the direction the system will travel in the next time step. Now let's take a closer look at the sensing and control. Each robot is identical and limited in its sensing capabilities, but we allow them to see a few key things within the environment, shown in the left diagram. They're able to observe the distances between themselves and the cylinder, which is RC, between themselves and the goal, which is RG, and between the cylinder and the goal, which is CG. We also let them see the angles between themselves and the goal, which is alpha, and between themselves and the cylinder, which is beta. Now, in terms of action space, we limit the robot's abilities to control their wheel speeds to incremental changes in wheel speeds called deltas. We allow them to change them up or down by 0.1 or maintain. Now, these deltas impose inherent momentum on the system, meaning that it takes time for the robots to speed up or slow down, and therefore it takes time for the object to speed up or slow down. Now this is key. This leads us to the novelty in this method, which is, can we learn to forecast the future heading of the system due to this momentum? Typically, this type of problem would be formalized as a decentralized, partially observable Markov decision process, where all the robots are interacting with each other directly. However, we model our problem as a single force, built of the individual forces by the robots, but being enacted by the cylinder itself. Therefore, the robots can directly interact with the cylinder rather than with all the other robots present. And this allows us to simplify our formulation to a partially observable Markov decision process, where an agent is acting on an object, and that object's reaction is accounted for in the transition dynamics, which is aided by our forecasted intention of the object's heading. We use a two-network neural architecture, where each network is comprised of 3 fully connected layers. The first network takes in positional data about the cylinder and outputs a forecast on the object's heading at the next time step. This heading is a value between -1 and 1, and you can think of this as a normalization between minus pi and pi. And this heading is then fed into the second network along with the robot's observations, and outputs an action for that robot to take at the next time step. Now we implement this in a centralized training, decentralized execution training scheme, meaning that all the robots contribute to the same model during training. And this trained model is then copied and placed on each robot individually for execution. Now here we show the benefit of the intention network through a behavioral analysis. The top left shows a 4-robot system without intention, failing to avoid the simple single cylinder obstacle. The same obstacle is easily avoided when intention is used, as shown in the top right. Now, the bottom left shows the system without intention making contact with both obstacles and bouncing off them. Now, in the bottom right, we show the system with intention avoiding the same obstacles with no contact. In the two-cylinder environment, the system without intention was able to solve with a success rate of 73.2%, whereas when we add intention, this rate jumps to 90.6%. We can also see that we learn faster, meaning less episodes. Without intention, it takes roughly 240 episodes to reach a usable policy. But when we add intention, we're able to reach a usable policy in roughly 60 episodes. So using our novel deep intention reinforcement learning method, we show increased behavioral dynamics, increased performance, and decreased training time over deep reinforcement learning methods without forecasting. We present a novel intention-based reinforcement learning method for aggregate robotics. Using intention, we're able to show emergent coordination despite the absence of explicit communication. The direct extension of this work is to explore how we can exploit communication to enhance intention. And the pressing question is, what do we communicate? For this, emergent language is of interest for the purpose of maintaining generality in aggregate robotics. This generality is important for modular robots and collective transport to allow for messages to take on different meanings specific to aggregates being trained. We will be implementing our method on a modular robotic platform and expanding our environment to allow for non-symmetrical objects as well as more difficult obstacles. We are excited about the direction of this work, and we thank you for your interest.